Hello, my name is Brandon Odell.
I'm Bridget Kerpies.
My name is Lugo.
And today we're going to be presenting our ME106 project, which is an automated mask.
So the goal of the project is because of the coronavirus, we have to wearing the mask all the time. So it's sometimes it really hard for the limited motion people. They are like they in the tough time to control the mask. So we decide to make the mask more personalized. We mount power display to sensor with the vehicle and to server on the mask to make it open and close the exhaust case, and also it can send whenever it's inside or outside by itself. And the more detail of the designs, Ritis can tell us about that. Yes, please.
Right. So we wanted a mask that had gills that can open and close based on user taps on an accelerometer. And we also wanted to use an ultrasonic sensor that can sense whether the user is indoor or outdoors. And we also wanted a display that could show what positions the flaps are in. And for our design targets, we wanted to keep the mask lightweight with evenly distributed weight to make it comfortable for the user to wear and make it easy to use so that people with limited hand motion are able to get the mask working well, and as well as making it efficient so that the flaps can open instantly whenever it's needed to be. Next slide. So yeah, this is the setup of our hardware. On the right, we have the mask with the servo and the 3D printed frames and flap. On the left, we have our sensors and display and Pico and breadboard setup. Next slide. And this is a more detailed diagram of what we had. We have the two sensors sending signals to Pico 1, and then those get sent to both servos. The servos are also connected to Pico 2 via the breadboard. And then the display also receives signals from the Pico to state whether the servos are in an open or closed position. And then we have the two power sources for the Pico itself. Next slide. So for the gills, we use SolidWorks to create frames that fits the mask and flaps that would act as the gills that can open and close with the servo. The left image is an isometric view of the servos with the flap connected to it and the frames that would be put on the mask. So the top view shows the servo in a closed position, and the bottom is the flap in an open position. So yeah, we used these designs and 3D printed them, and they were able to fit well with the mask and servos. Next.
Okay, so for the programming portion of this project, we originally wanted to go with a state machine, but we were unable to because of the pulse width modulated signal from the ultrasonic sensor. So instead, we just went with a basic while loop that basically would call on the accelerometer and check for taps. And then if the accelerometer got a tap, it would check into the distance function, which is shown at the right here. The distance function was responsible for checking if the user was inside or outside. At this time, the threshold value was set for 5 centimeters away from the ultrasonic sensor. This would determine inside or outside and would ultimately determine whether the mask was open or closed. Also inside of this loop, we would check for taps, and if the accelerometer was tapped, it would actually break out of this loop, which means it would stop checking the ultrasonic sensor, whether you're inside or outside, and it would solely it would just remain closed actually. And it would just also display, it was in the off state on our OLED display. And it also displays open and closed values as well. For our wire diagram, we wanted to show really which GPIO pins each sensor was connected to, including our actuators. So to start off, you can see that all of our signal wires are in orange and blue. So for this OLED, it is connected to GPIO pins 2 and 3. And you can actually see on here that those pins are responsible for I2C signals, which allows us to actually use the OLED. And then down here for the ultrasonic sensor, it is connected to pins 6 and 7. And you can see that those pins down here, 6 and 7, are capable of receiving a pulse width modulated signal. And then for the accelerometer, you can see that those are connected to 8 and 9, which are here and here, which are also capable of a pulse width modulated signal. And then we have the servos, which are connected to pins 21 and 22. You can check on this diagram. We have 21 and 22 here as shown, and those pins are also capable of pulse width modulation, which ultimately determines the angle of the servo, the angle of the servo's rotation.
Of our setup here. So right off the bat, as soon as you start up the program, it starts in the off state. So this means the flaps are going to be in the closed position. So if you look here, the flaps are actually closed while it's in the off state. And then we can double tap our accelerometer, and it'll convert our mask into the on state, which will either display open or closed. And then if we are in range of a roof, which currently is set at 5 centimeters, we will have our flaps closed. If we're not in range of a roof, which is greater than 5 centimeters, the flaps will remain open. And then if we also double tap again, this can deactivate the system completely and go back to closed flaps.
So overall, the automatic mask work really well. All functions are on track. The mask could properly send the AC inside or outside by itself, and this could not open these echoes. Yes, even if the user try to make it. Power display sensor and server work as expected. But however, in an actual products, to be more helpful to the limited, and we sell mount people on the wheelchair and wireless them with sensor and server. And definitely we have the tap control should be on the mask to make them more convenient. At the end of the day, the project I would like is to combine what we have learned from MA106, so that's the Pico, motor, server, and displays to make the work mechanism more valuable by becoming mechatronic. Next, please. Next, please. In short, because of these projects, I learned a lot. I learned more about the sensor, the server, also the display, and the most important things when I was doing the projects, my teammate helped me a lot. They helped me more understand about the wow look, the global values, and how it's interface with the main look. And Brandon, what did you learn from this project?
So from this project, I learned all the different signals that can be received and sent by our Picos. as well as the limitations of pulse width modulation in terms of when we went to program our state machine, it was much more difficult to have an interrupt from one of those signals. And then also the limited number of attachments that our Pico can have. So when we connected all of our sensors and all of our servos to one Pico, it wasn't able to operate correctly. And in a real life scenario, it'd be more likely that the Pico would be used for signal input and signal output only. So yeah, what about you, Bridget? What did you learn?
So I was able to learn how to interface different sensors, servos, and display with the Pico, and how they needed to be connected to specific groves. For example, the display needed to be connected to the groves that allowed it to receive I2C signals. Also, I was able to practice designing parts to be 3D printed so that it could fit snugly with our mask and servos. And in conclusion, we were able to meet our goals in keeping the mask lightweight, easy to use, and efficient with our working prototype. And that concludes our presentation. Thank you.